Tonight, we are going to talk about the planet you are lying on. Not the creatures that live on it, though some of them will appear before the night is through. Not the countries drawn across its surface or the cities that light it up when the sun goes down. Tonight, we are going deeper than that. We are going to talk about the thing itself. The rock, the water, the thin, improbable shell of air that wraps around it, like a breath that never quite lets go. You are lying on the surface of a sphere that is 12,742 kilometers wide. It weighs roughly 6,000 trillion kilograms, a number so large that writing it out would take more time than it is worth. So let us simply say that it is heavy beyond any human experience of heaviness. Beneath you, right now, there are layers of rock that stretch downward for thousands of kilometers, growing hotter and denser with every mile, until they reach a core of iron and nickel that burns at temperatures hotter than the surface of the sun. Above you, there is a column of air that extends upward for about 100 kilometers before it thins into nothing and gives way to the vacuum of space. You exist in the narrow margin between those two extremes. A sliver of habitable space so thin that if the Earth were the size of a basketball, the layer you live in would be thinner than a coat of varnish. And yet, here you are, breathing, comfortable, safe, held in place by gravity, warmed by a star that is 150 million kilometers away, shielded from the radiation of space by a magnetic field that you cannot see or feel, but that has been running without interruption for billions of years. Everything about your survival on this planet depends on systems so large and so old that they are easy to forget about entirely. The molten iron churning beneath the crust, the ocean currents that carry heat from the equator to the poles, the ancient bacteria that filled the atmosphere with the oxygen you are breathing right now, 2.5 billion years before anything with lungs existed to use it. Tonight, we are going to remember them. We're going to talk about what the Earth is made of, how it was formed, what has happened to it over 4.5 billion years of existence, and why, against considerable odds, it became the kind of place where someone like you could lie down at the end of a long day and listen to someone like me talk about it. If you are new to this channel, you are very welcome. You are welcome to close your eyes whenever you feel like it. You are welcome to let the words wash over you or to listen carefully, whichever suits the kind of evening you are having. There is nothing here that requires your concentration, only your company. And if you enjoy what you hear, a subscription would mean a great deal to us. Take a slow breath in. Let it fill your chest. Hold it gently for a moment and let it go. Let us begin. If you could dig a hole straight down from wherever you are right now, and if you could keep digging through every layer of rock and heat and pressure that stood in your way, you would need to travel approximately 6,371 kilometers before you reach the center of the Earth. That is roughly the distance from London to New York. It is a journey that no human being has ever made, that no machine has ever come close to completing, and that no technology currently in existence could survive. The deepest hole ever drilled into the Earth was a Soviet project called the Kola Super Deep Borehole, begun in 1970 on the Kola Peninsula in the far northwest of Russia. For nearly 20 years, engineers worked to push a drill bit deeper into the crust than anyone had ever gone before. They reached 12.2 kilometers, and then they stopped. Not because they chose to, but because the Earth would not allow them to continue. The rock at that depth had reached over 180 degrees Celsius, far hotter than anyone had predicted, and it behaved less like a solid and more like a kind of geological putty, deforming under pressure, closing the borehole almost as fast as it could be drilled. The drill bits softened and broke. The rock flowed. 12 kilometers down, the Earth said no. 12.2 kilometers. That sounds impressive until you consider the numbers. The distance to the center of the Earth is 6,371 kilometers. The Kola borehole reached less than 0.2% of that distance. If the Earth were a human body, the borehole would not have made it through the skin. We reached in the most ambitious drilling project in human history, barely past the outermost edge of the outermost layer. And yet, we know what is down there. We know with remarkable precision, not because anyone has seen it, but because the Earth tells us every time it shakes. When an earthquake occurs, it sends waves of energy rippling through the interior of the planet. These seismic waves travel at different speeds depending on what they are passing through. They move faster through dense material and slower through less dense material. They bend when they cross a boundary between two different types of rock. Some types of waves, called P waves, can pass through both solids and liquids. Others, called S waves, can only travel through solids, and they stop dead when they encounter liquid. By studying the way these waves arrive at seismograph stations around the world, measuring their speed, their angle, their timing, and most importantly, which ones arrive and which ones are conspicuously absent, scientists have assembled a remarkably detailed picture of the Earth's interior without ever having to go there. It is a form of imaging not entirely unlike a medical scan, except the patient is a planet, and the scan takes the form of its own tremors. What that picture reveals is a world of layers, each one more extraordinary than the last. The outermost layer, the one you are most familiar with, is the crust. It is the thinnest layer by a considerable margin. Beneath the continents, it ranges from about 30 to 70 kilometers thick. Beneath the oceans, it is much thinner, only 5 to 10 kilometers in most places. The crust is where everything you have ever known has taken place. Every mountain, every valley, every ocean trench, every city, every forest, every road you have ever driven on. All of it sits within this thin outer shell, which in planetary terms is roughly comparable to the skin on an apple. If you have ever held an apple in your hand and run your thumb across its surface, you have felt something that, in proportion, is thicker than the layer of rock that separates you from the deep interior of the planet. Beneath the crust lies the mantle, and the mantle is where the Earth begins to become truly strange. It extends downward for nearly 2,900 kilometers, making it by far the thickest layer, comprising roughly 84% of the Earth's total volume. The mantle is not liquid despite what many people believe. It is solid rock. But it is solid rock under such immense heat and pressure that over long timescales it flows incredibly slowly, like toffee that has been left in the sun. If you could watch the mantle in time-lapse, speeding up millions of years into minutes, you would see it churning. Great columns of hot rock rising from the depths and cooler rock sinking back down, a slow-motion convection that looks almost like a pot of thick soup on a low flame. The temperature in the mantle ranges from about 500 degrees Celsius near the top to nearly 4,000 degrees near the bottom. It is a place of unimaginable heat contained within rock that moves at the pace of a growing fingernail. A centimeter or two per year, the speed barely perceptible even across a human lifetime, but devastating across geological time. And then, beneath the mantle, we reach the core. And the core is where the Earth becomes something else entirely. The outer core is a churning ocean of liquid iron and nickel, roughly 2,200 kilometers thick. The temperature here ranges from 4,000 to over 5,000 degrees Celsius. It is hotter than the surface of the sun, and this liquid metal is not still. It moves. Driven by heat rising from the inner core below and the rotation of the Earth itself, the liquid iron flows in vast, complex convection currents, rising and sinking and swirling in patterns that scientists are still working to fully understand. These currents are responsible for something that you depend on every moment of your life, whether you know it or not. They generate the Earth's magnetic field. The process is called the geodynamo, and it works on the same basic principle as an electrical generator. When a conducting fluid, in this case liquid iron, moves through an existing magnetic field, it produces electrical currents. Those electrical currents in turn generate their own magnetic field, which reinforces the original field, which drives more currents, which generate more magnetism. It is a self-sustaining loop, a feedback system that has been running for at least 3.5 billion years, powered by nothing more than heat and rotation and the movement of liquid metal in the dark. The magnetic field it produces extends far out into space, forming a protective bubble around the Earth called the magnetosphere. This invisible shield deflects the solar wind, a constant stream of charged particles blasted outward from the sun at speeds of up to 800 kilometers per second. Without the magnetosphere, the solar wind would strip away the Earth's atmosphere molecule by molecule, the way it stripped the atmosphere from Mars. Mars once had a magnetic field. It lost it roughly 4 billion years ago when its core cooled and solidified, and the dynamo stopped. Within a few 100 million years, Mars lost most of its atmosphere. Its oceans evaporated into space. Its surface became the cold, barren, radiation-blasted desert that we see today. Mars is what happens when the dynamo fails. Earth is what happens when it does not. At the very center of everything, at the absolute heart of the planet, sits the inner core. It is a solid ball of iron and nickel, approximately 2,440 kilometers in diameter, roughly the size of the Moon. Despite being hotter than the outer core, it is solid because the pressure at the center of the Earth is so extreme, over 360 gigapascals, that the iron atoms are forced into a crystalline structure that cannot melt regardless of the temperature. It is the hottest place on the planet and also the most compressed, a paradox of physics that exists nowhere else we know of. And there is one more detail about the inner core that is worth holding in your mind as you settle deeper into the quiet of this evening. The inner core rotates, not at the same speed as the rest of the Earth, but slightly faster, gaining on the surface above it by a fraction of a degree each year. The planet you are lying on is not a single spinning object. It is a set of nested spheres, each one turning at its own pace, the innermost outrunning the outermost by a tiny margin that accumulates over millions of years. You are riding on the outside of a system that is moving in ways you cannot feel, driven by forces you cannot see, sustained by a ball of iron the size of the Moon that sits 6,000 kilometers below your pillow and has been burning quietly since before life existed. It is, by any measure, a remarkable thing to be lying on top of. The ground beneath you feels solid. It feels permanent. If you were to step outside right now and stand on the Earth, you would feel something firm and unmoving under your feet. And every instinct you have would tell you that it has always been this way. The ground does not move, the continents do not drift. The mountains have always been where they are. This is what the world feels like when you are standing on it. And for most of human history, it was what everyone believed. They were wrong. The ground moves. It has always moved. In 1915, a German meteorologist named Alfred Wegener published a hypothesis that the continents had once been joined together in a single landmass, which he called Pangaea, meaning all lands, and had since drifted apart to their current positions. his evidence was compelling. The coastlines of South America and Africa fit together like pieces of a jigsaw puzzle. Identical fossils of the same ancient reptile, Mesosaurus, had been found on both sides of the Atlantic, in rocks of exactly the same age, in places now separated by thousands of kilometers of open ocean. Geological formations that ended abruptly at the coast of one continent continued seamlessly on the coast of another. The evidence was everywhere, written in the rocks and the fossils and the shape of the land itself. The scientific establishment rejected him almost completely, not because the evidence was weak, but because Wegener could not explain the mechanism. He could show that the continents had moved, but he could not say how. What force could possibly push something as massive as a continent across the surface of the Earth? Without an answer to that question, the hypothesis was dismissed as fanciful, the daydream of a meteorologist who should have stayed in his own lane. Wegener died in 1930 on an expedition in Greenland without ever seeing his idea accepted. It would take another 3 decades before the mechanism was understood. The answer was plate tectonics, and it changed everything we thought we knew about the surface of the Earth. The Earth's outer shell, the crust, and the uppermost portion of the mantle together form a rigid layer called the lithosphere. This layer is not a single unbroken surface. It is cracked into enormous pieces called tectonic plates that fit together like the panels of a football. There are 7 major plates and several smaller ones, and every continent, every ocean, every island, every square meter of the Earth's surface sits on one of them. These plates are not stationary. They move, driven by the slow convection currents in the mantle beneath them. The fastest plates move at roughly 15 centimeters per year, about the speed at which your fingernails grow. The slowest creep along at barely 1 centimeter. But over millions and billions of years, these tiny movements add up to journeys of thousands of kilometers. Where plates move apart, new crust is born. Along the mid-ocean ridges, vast underwater mountain chains that wind through every ocean on Earth for a combined length of over 65,000 kilometers. Magma rises from the mantle to fill the gap left by the separating plates. It cools, solidifies, and becomes new ocean floor. The mid-Atlantic ridge, the most famous of these, runs down the center of the Atlantic Ocean from the Arctic nearly to Antarctica. It is the seam where the North American plate and the Eurasian plate are pulling apart, and it is the reason the Atlantic Ocean exists. 200 million years ago, there was no Atlantic. North America, Europe, and Africa were joined. Then the rift began. The plates started to separate. Magma filled the crack, and an ocean was born. It has been growing ever since. Right now, at this moment, the Atlantic is getting wider by about 2.5 centimeters per year. London and New York are 2.5 centimeters further apart tonight than they were a year ago. You will never notice it. The ocean does not care whether you notice it. It simply grows. Where plates come together, the results are more dramatic. When 2 plates carrying continental crust collide, neither one can sink beneath the other because continental crust is too buoyant, too thick, too light. Instead, the crust crumples and folds and rises, pushed upward by the relentless pressure of 2 land masses driving into each other. The Himalayas exist because the Indian plate has been driving into the Eurasian plate for roughly 50 million years. The collision has pushed the crust upward by nearly 9 kilometers at its highest point, and it has not stopped. The Himalayas are still rising, still growing taller by a few millimeters each year. Everest is higher tonight than it was a century ago. When an oceanic plate meets a continental plate, the denser oceanic plate is forced downward, diving beneath the continent in a process called subduction. It descends into the mantle, heats up, and partially melts. Some of that molten rock rises back through the crust and erupts. This is where most of the world's volcanoes come from. The ring of fire encircling the Pacific Ocean is the direct result of oceanic plates being subducted along almost the entire Pacific rim. 75% of the world's active volcanoes sit along this ring. It is the most geologically violent region on the planet, and that word, recycled, is the key to understanding plate tectonics. It is not just a system that moves continents around, it is a recycling system. Old ocean floor is created at mid-ocean ridges, spreads outward over millions of years, and is eventually consumed at subduction zones, dragged back into the mantle where it melts and mixes and will eventually rise again as new magma. The cycle takes roughly 200 million years. This is why no ocean floor on Earth is older than about 200 million years, even though the planet itself is 4.5 billion years old. The surface is constantly being replaced. The old is swallowed, the new is born. This is what makes Earth unique. Mars has no plate tectonics. Its surface is ancient and frozen in place. The Moon is the same. Venus, Mercury, every rocky body we have examined carries a surface that records billions of years of history because nothing has come along to wipe the slate clean. Earth is different. Earth erases its own history and writes a new one, over and over in a cycle that has been running since the planet was young. And the continents have not simply sat in one place for all that time. They have wandered. Driven by the same plate movements that open and close oceans, the continents have assembled into supercontinents and broken apart again at least 5 times. Pangaea, the one most people know, existed roughly 300 million years ago. But before Pangaea, there was Pannotia. Before Pannotia, Rodinia. Before Rodinia, Columbia. Before Columbia, Kenorland. Each supercontinent, formed over hundreds of millions of years, existed as a single vast landmass, and then rifted apart. The cycle takes roughly 500 million years. In another 250 million years, models suggest the continents will form a new supercontinent that some scientists have already named Pangaea Ultima. The Mediterranean will close, the Atlantic will close, Africa will merge with the Eurasia. The world will be unrecognizable. You are lying on a planet that takes itself apart and puts itself back together again, on a timescale so vast that entire species evolve and go extinct between one arrangement of the continents and the next. The ground beneath you is not permanent. It is a temporary surface, a thin and restless skin on a world that has never stopped moving. The engine that drives all of it will keep turning for another 4 or 5 billion years. Plenty of time. If you could drive a car straight up at motorway speed, you would leave the atmosphere in about an hour. That is all that separates you from the vacuum of space. 1 hour of driving. A thin, fragile, almost negligibly narrow envelope of gas, clinging to the surface of a rocky planet by nothing more than gravity. It is, by any reasonable measure, not very much, and it is the only reason anything on this planet is alive. The atmosphere is mostly nitrogen. 78% of every breath you take is nitrogen, a gas that your body does essentially nothing with. You breathe it in and you breathe it out, unchanged, a passive passenger in every respiratory cycle you have ever completed. 21% is oxygen, and this is the part that matters, the part your lungs extract and your blood carries and your cells burn to produce the energy that keeps you thinking and breathing and listening to these words. The remaining 1% is a scattering of other gases, argon mostly, with trace amounts of carbon dioxide, neon, helium, and water vapor. Carbon dioxide currently makes up about 0.04% of the atmosphere. That is almost nothing. It is enough to determine the temperature of the entire planet. The atmosphere is not a uniform blanket. It is a series of layers stacked on top of one another, like the floors of a building with no walls. The lowest layer, the one you live in, is the troposphere. It extends from the surface to roughly 12 kilometers and contains approximately 80% of the atmosphere's total mass and virtually all of its weather. Every cloud you have ever seen, every rainstorm, every snowfall, every bolt of lightning, every hurricane, every gentle breeze that has ever moved across your face, all of it happened in the troposphere. Temperature drops as you ascend, falling by roughly 6.5 degrees Celsius for every kilometer of altitude, until at the top, the air is 50 or 60 degrees below zero. Above the troposphere lies the stratosphere, extending to about 50 kilometers. This is where the ozone layer lives, a thin band of triatomic oxygen that absorbs the majority of the sun's ultraviolet radiation before it reaches the surface. If you compressed all the ozone in the atmosphere into a single layer at sea level pressure, it would be roughly 3 millimeters deep. 3 millimeters. That is the shield between you and radiation levels that would cause severe burns within minutes of exposure. In the context of a planet 12,000 kilometers wide, 3 millimeters is almost nothing. And yet, it is enough because chemistry does not care about thickness, only about whether the right molecules are in the right place to intercept the right wavelengths of light. Above the stratosphere, the mesosphere, where temperatures drop again and meteors burn up in bright streaks as they collide with air molecules at tremendous speed. Then the thermosphere, where the air is so sparse that individual molecules can travel kilometers between collisions, and temperatures measured by the kinetic energy of those molecules can exceed 2,000 degrees Celsius, even though you would feel bitterly cold, because there is simply not enough matter to transfer heat to your skin. This is where the International Space Station orbits and where the aurora dances. Beyond the thermosphere, the exosphere fades into the vacuum of space. There is no hard boundary, no door marked exit. The atmosphere simply thins, molecule by molecule, until there is nothing left. The air you are breathing right now has been breathed before, not in a metaphorical sense, in a literal, molecular sense. The Earth does not produce new atmosphere, it recycles what it has. The same molecules of nitrogen and oxygen that exist today have been circulating through lungs and leaves and oceans and soil for billions of years. Every breath is borrowed from a supply that was established long before you arrived and will continue long after you are gone. And the oxygen itself has a history that is almost too dramatic to believe. For the first 2 billion years of Earth's existence, there was virtually no free oxygen in the atmosphere. The air was a mix of nitrogen, carbon dioxide, methane, and water vapor, an atmosphere that would kill any modern animal within minutes. Then, roughly 2.4 billion years ago, something changed. But that is a story for later. For now, it is enough to know that if the Earth were slightly closer to the Sun, the oceans would have boiled, and the atmosphere would have become a choking blanket of steam and carbon dioxide, the way it did on Venus. If it were slightly further away, the water would have frozen, and the atmosphere would have thinned to almost nothing, the way it did on Mars. The Earth sits in the narrow band between these two fates, a position so precise that scientists have given it a name that sounds like a fairy tale. The Goldilocks zone. Not too hot, not too cold, just right. You are breathing inside a fairy tale that happens to be true. And the thin blue line that astronauts see from orbit, that impossibly slender glow curving along the edge of the Earth against the blackness of space, is not much, but it is everything. The Earth is, by any honest visual assessment, a water planet. Seen from space, the land is an afterthought, Continents and islands sit like patches of brown and green on a surface that is overwhelmingly, almost absurdly, blue. 71% of the planet is covered by ocean, and that ocean contains 1.335 billion cubic kilometers of water, a volume so vast that if you gathered it into a sphere, it would measure roughly 1,385 kilometers across, about the distance from London to Rome. It sounds enormous, and it is. But spread thin across a planet nearly 13,000 kilometers wide, it is remarkably shallow. The average depth of the ocean is 3.7 kilometers. The planet's diameter is nearly 13,000. The ocean is a thin film of water draped across the surface, no deeper in proportion than the dew on the skin of a plum. It feels boundless when you stand at its edge. It is not. It is a remarkably thin layer of liquid balanced on the surface of a very large rock, held in place by gravity, prevented from boiling away by the atmosphere above, and prevented from freezing solid by the heat of the sun and the circulation of the water itself. That circulation is one of the most important systems on Earth. The ocean is not still. It moves constantly, driven by wind at the surface and by differences in temperature and salinity in the deep. The system that connects these deep movements is called the thermohaline circulation, and it operates like a vast, slow conveyor belt that carries water around the entire planet. In the North Atlantic, near Iceland and Greenland, surface water is cooled by the Arctic air. As it cools, it becomes denser. If it is also saltier than usual, which happens when sea ice forms and leaves its salt behind, it becomes denser still. Eventually, it is heavy enough to sink. It plunges from the surface to the deep ocean, dropping to depths of several thousand meters, and begins a slow journey southward along the floor of the Atlantic. It creeps past the equator, rounds the southern tip of Africa, and enters the Indian and Pacific Oceans, still deep, still cold, still moving at a pace measured in centimeters per second. Eventually, sometimes centuries later, it rises back to the surface, warmed by the sun, and begins the long return journey. The complete circuit, from the moment a parcel of water sinks in the North Atlantic to the moment it returns, takes approximately 1,000 years. A molecule of water that sank near Greenland during the reign of William the Conqueror is only now completing its journey back to the surface. The ocean absorbs more carbon dioxide than all the forests on Earth combined. It absorbs enormous quantities of heat, buffering the planet from the full force of solar radiation. Without the ocean's capacity to store and redistribute heat, the temperature differences between the equator and the poles would be far more extreme, and the climate of every continent would be radically different. It also produces more than half the oxygen you breathe, generated by phytoplankton so small that a single drop of seawater may contain thousands of them. These microscopic organisms, invisible to the naked eye, collectively produce more oxygen than every forest on the planet, and we have explored almost none of it. The figure commonly cited is 5%, though estimates vary. What is not in dispute is that more of the Moon's surface has been mapped in high resolution than the floor of the Earth's own ocean. The Challenger Deep, at the bottom of the Mariana Trench, sits nearly 11 kilometers below the surface. Mount Everest could be placed inside it, and its summit would still be more than a kilometer underwater. Only 3 crewed missions have ever reached the bottom. The first, in 1960, carried 2 men in a vessel called the Trieste. They stayed for 20 minutes. The ocean covers most of the world. It drives the climate. It generates half your oxygen. It is the largest habitat on the planet, home to the tallest mountains, the deepest valleys, and the longest mountain chain on Earth. And it is, for all practical purposes, unknown. We live on a water planet and we have barely begun to understand the water. It is, if you think about it, a comforting thought. There is still so much left to find. 4.5 billion years ago, the Earth was not the planet you know. It was young, barely formed, its surface a churning sea of molten rock, glowing orange and red beneath an atmosphere thick with steam and carbon dioxide. There were no oceans. There was no solid ground. There was only heat and the slow process of a planet trying to cool itself down. And then something hit it. The object was roughly the size of Mars, a body so large that calling it an asteroid does not do it justice. Scientists have given it a name, Theia, after the Greek goddess who was the mother of the moon. Theia had been sharing Earth's orbital neighborhood for millions of years, gravitationally nudged by the other planets, its path growing less stable with each passing orbit, until one day the mathematics of celestial mechanics ran out of room for compromise, and the two worlds collided. The impact was not like anything you can compare to an earthly experience. There is no explosion, no collision, no disaster in human history that offers a useful frame of reference. The energy released was so vast that both bodies were effectively destroyed. The solid surfaces of both planets were liquefied instantly. Their mantles merged. Their cores, dense balls of iron, spiraled into each other and combined. The temperature at the point of impact exceeded 10,000 degrees Celsius. A cloud of vaporized rock and molten debris was blasted outward into space, forming a vast disk of superheated material that orbited the ruined Earth like a ring of fire. Within hours, the planet that had existed before the impact was gone. In its place was something larger, hotter, and entirely molten, spinning fast, surrounded by a disk of debris that stretched tens of thousands of kilometers into space. And within that disk, something was already beginning to happen. The debris was cooling. Droplets of molten rock were colliding and sticking together. Larger clumps attracted smaller ones. Gravity, patient and relentless, was pulling the scattered material into a sphere. Within a few thousand years, perhaps less, the disk had coalesced into a single body. The Moon. The evidence for this is written in the rocks that the Apollo astronauts brought home. The isotopic signatures of lunar samples, the ratios of different forms of oxygen and titanium and other elements, are nearly identical to those found in Earth's mantle. The Moon is not a captured asteroid. It is not a body that formed independently elsewhere in the solar system. It is made from the same material as the Earth itself, blasted free by the impact and reassembled in orbit. The Moon is a piece of the Earth that was knocked loose and never came back. And the Moon, once formed, changed everything. It stabilizes the Earth's axial tilt. The Earth is tilted at approximately 23.5 degrees relative to its orbital plane. And this tilt is what gives us seasons. Without the Moon's gravitational influence, this tilt would not remain stable. It would wobble chaotically over millions of years, swinging from nearly 0 degrees, which would eliminate seasons entirely, to as much as 45 degrees or more, which would produce climate extremes that could make complex life impossible. Mars, which has no large moon, experiences exactly this kind of axial wobble, and its climate history has been correspondingly erratic. The Moon acts as a gravitational anchor, a stabilizer that keeps the Earth's tilt within a narrow, life-friendly range. It has been doing this for 4.5 billion years. The Moon also drives the tides. Its gravitational pull on the Earth's oceans creates bulges of water on opposite sides of the planet. And as the Earth rotates beneath these bulges, the water rises and falls along every coastline in a rhythm that has been running since the oceans first formed. Tides may have been essential to the origin of life itself. The repeated wetting and drying of tidal pools creates exactly the kind of concentrated chemical environment where complex organic molecules can form, break apart, and recombine in new configurations. Some researchers believe that life began not in the deep ocean, but in those shallow, churning, tidally driven margins where land meets sea, a process that could not have happened without the moon. The moon is drifting away slowly, at a rate of about 3.8 centimeters per year. In the deep past, it was much closer, and the tides were much stronger, and the days were much shorter. 1 billion years ago, a day on. Earth lasted only 18 hours. The moon's gravitational drag on the oceans has been gradually slowing the Earth's rotation ever since, trading the planet's spin for orbital distance, a transaction so slow that it will take billions more years to complete. You can see it tonight if the sky is clear. A pale disk of reflected sunlight hanging in the dark, looking as though it has always been there. It has not. It was born in violence, forged from the wreckage of a collision that nearly destroyed the planet, assembled from a ring of fire that circled the wounded Earth like a halo. And every tide, every stable season, every predictable climate cycle that has allowed life to flourish on this planet owes something to that catastrophe. The worst day in Earth's early history may have been the most important thing that ever happened to it. Between roughly 720 million and 635 million years ago, something happened to the Earth that almost ended the story of life before it had properly begun. The planet froze, not partially, not in the way that ice ages typically work, with glaciers advancing from the poles while the tropics remain warm and green and full of life. This was different. This was total. The ice advanced from both poles simultaneously, creeping across the temperate zones, crossing the tropics and meeting at the equator. The entire surface of the Earth, land, and ocean alike was encased in ice. The oceans were sealed beneath a frozen shell that may have been a kilometre thick in places. The average global temperature dropped to approximately -50 degrees Celsius. The planet, seen from space, would have been white, a snowball. The cause was almost certainly a runaway feedback loop involving ice and sunlight. Ice is white. White surfaces reflect sunlight back into space rather than absorbing it as heat. As the ice sheets expanded from the poles, they reflected more solar energy, which cooled the planet further, which caused more ice to form, which reflected more sunlight, which cooled the planet further still. Once the ice reached a critical latitude, somewhere around the tropics, the feedback became unstoppable. The planet tipped into a frozen state from which there was, under normal circumstances, no obvious way back. Life did not end. It came close, but it did not end. Somewhere beneath the ice, in pockets of open water near volcanic vents on the ocean floor, in thin cracks where geothermal heat kept the water liquid, microorganisms survived. They clung to existence in conditions that would seem impossible by any modern standard, waiting out a winter that lasted not months or years, but tens of millions of them. And it was volcanoes that eventually broke the spell. This is the part that reveals the extraordinary self-correcting nature of the Earth as a system. Even while the surface was frozen solid, volcanoes continued to erupt. They had no reason to stop. Volcanic activity is driven by the mantle, and the mantle does not care what is happening on the surface. Carbon dioxide poured from volcanic vents into the atmosphere, year after year, century after century, millennium after millennium. Under normal conditions, this CO2 would be absorbed by the oceans and by the chemical weathering of rocks. But the oceans were sealed under ice. The rocks were buried. The normal carbon sinks were shut down, and so the carbon dioxide accumulated with nothing to remove it, building over millions of years until the greenhouse effect became so powerful that even the reflective ice could not hold it back. The thaw, when it came, was catastrophic in the opposite direction. The ice began to melt, exposing dark ocean water that absorbed sunlight instead of reflecting it, which warmed the planet further, which melted more ice, which exposed more water. The same feedback loop that had frozen the Earth now ran in reverse, and it ran fast. The planet swung from deep freeze to extreme hothouse in what, geologically speaking, was an instant. Temperatures soared. Rain fell on exposed rock for the first time in millions of years, washing minerals and nutrients into the sea at rates that would have been unprecedented. And then something remarkable happened. In the aftermath of Snowball Earth, life did not merely recover, it exploded. Within a few tens of millions of years of the final thaw, the fossil record shows a dramatic surge in biological diversity. New forms of multicellular life appeared. Body plans that had never existed before emerged in rapid succession. Many scientists believe that the Cambrian explosion, the sudden appearance of nearly all major animal groups roughly 540 million years ago, was at least partly triggered by the extreme selective pressures of the Snowball Earth period. Life that had been forced to survive in desperate conditions for millions of years emerged tougher, more adaptable and ready to diversify into every available niche. The worst crisis in the history of life may have been the catalyst for the greatest creative burst it has ever produced. The Earth froze, and life nearly died. The Earth thawed, and life reinvented itself. It is a pattern you will see again and again in the history of this world. Destruction followed by renewal. Catastrophe followed by innovation. A planet that breaks itself and puts itself back together, each time a little different, each time a little more complex than before. 66 million years ago, on an otherwise ordinary day in the late Cretaceous period, an asteroid approximately 12 kilometers across entered the Earth's atmosphere at a speed of roughly 72,000 kilometers per hour. It had been traveling through space for millions of years, following an orbital path that had been slowly, imperceptibly converging with the Earth's. By the time it was close enough to be visible in the sky, there were only seconds left. There was no warning. There was no time for anything to react. It struck what is now the Yucatan Peninsula of Mexico in shallow coastal waters, and the energy released was equivalent to approximately 10 billion nuclear weapons detonating simultaneously. A crater 180 kilometers wide and 20 kilometers deep was blasted into the crust. The shockwave radiated outward, flattening everything within 1,500 kilometers. The air itself became superheated. Tsunamis hundreds of meters tall swept across the Atlantic and the Gulf of Mexico, striking coastlines thousands of kilometers away with a force that rearranged the geology of entire regions. But the immediate destruction, as staggering as it was, killed relatively few species. What followed was worse. The impact launched billions of tons of pulverized rock and soot into the upper atmosphere, where it spread around the globe within days. The sky darkened. Sunlight, which had driven the food chain of the entire planet for billions of years, was blocked. Temperatures plummeted. Photosynthesis collapsed. Plants died. The herbivores that depended on them starved. The carnivores that depended on the herbivores starved in turn. The food chain was not weakened, it was severed at its base. The darkness lasted months, possibly years. When it finally cleared, the world that emerged was unrecognizable. 75% of all species on Earth had gone extinct, including every non-avian dinosaur. The creatures that had dominated the planet for over 160 million years were gone. Not gradually, not over millions of years of slow decline, but in what amounted to a geological instant. But not everything died, and this is where the story turns. Small mammals survived. They were burrowers, many of them, insulated from the worst of the cold, capable of surviving on seeds and insects and fungi when larger food sources disappeared. Birds survived, the last living descendants of the dinosaurs, carrying the genetic legacy of their ancestors into a world that had just been emptied. Crocodilians survived in the water. Turtles survived. Sharks, which had already been swimming the oceans for hundreds of millions of years before the dinosaurs even appeared, barely noticed. The extinction reset the evolutionary clock. Every ecological niche that the dinosaurs had occupied for 160 million years was suddenly vacant. Every role in every ecosystem was open, and the survivors filled them. Mammals, which had spent the entire age of the dinosaurs as small, nocturnal, marginal creatures, diversified with extraordinary speed. Within 10 million years of the impact, they had radiated into bats, whales, horses, primates, and hundreds of other forms. The age of mammals had begun not because mammals were superior, but because a rock from space had cleared the stage. Every mammal alive today exists because of that asteroid. If it had arrived 10 minutes earlier or 10 minutes later, the rotation of the Earth would have placed a different patch of surface beneath it. If it had been slightly smaller, the extinction might not have been severe enough to unseat the dinosaurs. If slightly larger, it might have sterilized the planet entirely. The window between not enough destruction and too much was narrow, and the asteroid threaded it precisely. The crater still exists, buried beneath a kilometre of limestone. It is called Chicxulub, after the nearest town, a name that derives from a Mayan phrase meaning the tail of the devil. It is, depending on your perspective, the worst or the best thing that ever happened to this planet. Probably both. The worst mass extinction in Earth's history was not caused by an asteroid or a volcano or a sudden freeze. It was caused by a gas that you are breathing right now, that your body depends on for every moment of its existence, and that without you would die within minutes. Oxygen. 2.5 billion years ago, oxygen was poison. For the first 2 billion years of Earth's existence, the atmosphere contained virtually no free oxygen. The organisms that existed, all of them microscopic, all single-celled, were anaerobic. They had evolved to live without oxygen, and oxygen, if introduced, would have destroyed them, reacting with their cellular chemistry the way oxygen causes iron to rust. Then, cyanobacteria evolved the ability to harvest energy from sunlight using water and carbon dioxide. The process released oxygen as a byproduct. At first, this did not matter. The oxygen was immediately absorbed by the environment. It reacted with dissolved iron in the oceans, forming iron oxides that sank to the seafloor in vast layers of rust-colored sediment. These banded iron formations are still visible today, striped bands of red and grey in ancient rock that tell the story of an ocean slowly rusting from the inside out. For hundreds of millions of years, the Earth absorbed every molecule of oxygen the cyanobacteria produced. The sinks held until they didn't. The iron was used up, the rocks were saturated, the methane was consumed. There was nothing left to absorb the oxygen, and it began to accumulate in the atmosphere. For the anaerobic organisms that had been the only life on Earth for 2 billion years, this was the end. The Great Oxidation Event killed the vast majority of anaerobic life on the planet. An entire biosphere, the dominant form of life for longer than complex life has existed in total, was poisoned by the waste product of its neighbors. It is the longest and most thorough mass extinction the Earth has ever experienced. The survivors adapted. Some retreated to environments where oxygen could not reach. The deep ocean floor, the insides of rocks, the oxygen-free mud at the bottom of lakes. Others evolved a revolutionary new trick. Instead of being destroyed by oxygen, they learned to use it. Aerobic respiration, burning oxygen to produce energy, was roughly 18 times more efficient than anything that had come before. This enormous surplus of energy would eventually make possible everything that followed. Muscles that could move quickly, nervous systems that could process information, brains that could think. Every complex organism on Earth runs on aerobic respiration. Every one of them owes its existence to a metabolic pathway that evolved as a survival response to an oxygen catastrophe 2.5 billion years ago. The breath that sustains you is made of the same gas that once nearly ended all life on Earth. What was poison became fuel. What was catastrophe became possibility. The worst things that happen to the Earth are often the things that make it ready for what comes next. Beneath the crust, the mantle moves. Not quickly. Not in any way that you would recognize as movement if you were somehow able to watch it. The mantle moves the way a glacier moves, the way continents drift, the way mountains rise. It moves on a timescale so far removed from human experience that calling it slow does not begin to capture it. A centimeter per year, perhaps 2, the speed at which your hair grows. But it is churning. And that slow, patient movement is responsible for nearly every large-scale feature on the surface of the planet. The mantle is solid rock, heated to temperatures between 500 and 4,000 degrees Celsius, placed under pressures so enormous that it cannot melt despite the heat. Instead, it deforms. It flows. Given enough time and enough force, solid rock behaves like an extraordinarily thick fluid, rising where it is heated, sinking where it cools, circulating in vast loops called convection cells that span hundreds of kilometers and take millions of years to complete a single rotation. These convection cells are the engine of everything. They drive the tectonic plates. They pull old ocean floor down at subduction zones and push new ocean floor up at mid-ocean ridges. They build mountains. The Himalayas exist because of mantle convection. The Indian plate, carried northward by currents deep beneath the surface, has been driving into the Eurasian plate for 50 million years. The collision has crumpled the crust upward, folding and stacking layers of rock like a tablecloth pushed across a table. Everest, the highest point on Earth at 8,849 meters, is made largely of marine limestone. There are fossils of sea creatures near its summit, organisms that lived on the floor of an ancient ocean called Tethys that once separated India from Asia. The highest place on land is made of rock that formed at the bottom of the sea. The mantle carried it there. The longest mountain range on Earth is not on land at all. The mid-ocean ridge system winds through every ocean for over 65,000 kilometers. It is a continuous chain of underwater mountains and rift valleys that most people will never see. Yet, it is the single largest geological feature on the planet. More magma erupts along the mid-ocean ridges each year than from all the land-based volcanoes combined. The Earth is building new surface constantly, quietly, in the dark, at the bottom of the sea. And where plates dive beneath one another, the recycled rock descends, heats up, partially melts, and some of it rises again to erupt at the surface. The Ring of Fire, encircling the Pacific, contains 75% of the world's active volcanoes, and generates 90% of its earthquakes. Indonesia sits atop 3 colliding plates and contains more than 130 active volcanoes. Japan sits on 4 plates. Iceland sits directly on top of the mid-Atlantic ridge, one of the only places on Earth where a mid-ocean ridge rises above the surface. The island is literally being pulled apart, growing wider by a few centimeters each year, built from the magma that wells up from the rift between 2 separating continents. The surface of the Earth is not a finished product. It is a work in progress shaped by forces that operate on timescales so long that the rise and fall of entire civilizations fits between one measurable change and the next. The mountains you see today will not be the mountains that exist 100 million years from now. They will have eroded to plains, and new mountains will have risen somewhere else, pushed up by the same rivers of stone that built these ones. There is no final arrangement. There is only the slow, ceaseless, patient rearrangement of the surface by the heat below. Let us follow a single molecule of water. It is falling right now as rain over the eastern slopes of the Andes in Peru. It has been a cloud for the last 9 days, drifting westward across the Atlantic from the coast of Africa, picking up moisture from the warm tropical ocean below, climbing as it reached the South American continent, cooling as it rose until the air could hold it no longer, and it fell. It lands on a hillside thick with vegetation, soaks into the soil, trickles downward through layers of clay and rock, and emerges days later as a small spring that feeds a stream, that feeds a tributary, that feeds the Amazon. It spends 3 months in the river, moving slowly through the largest freshwater system on Earth, past flooded forests and sandbars and pink river dolphins, until it reaches the Atlantic Ocean near the city of Belém. It mixes with the salt water. It sinks. Carried by the thermohaline circulation, it descends to the deep ocean, where it will spend the next 800 years moving through the cold, dark waters of the abyss, traveling south along the floor of the Atlantic, rounding the tip of Africa, drifting through the Indian Ocean, and eventually rising to the surface somewhere in the Pacific, warmed by the sun for the first time in centuries. It evaporates. It becomes a cloud. It falls again, perhaps on a mountainside in Japan, perhaps on an open field in Australia, perhaps on the roof of a building in a city that does not yet exist. This is the water cycle, and its most extraordinary feature is not its complexity, but its permanence. The Earth does not create new water. It does not lose old water. Every molecule of water that exists on this planet has been here for approximately 4.5 billion years. The water you drank this morning has been rain, river, ocean, ice, cloud, steam, snow, and fog more times than anyone could calculate. It has been inside the cells of organisms that went extinct before the dinosaurs appeared. It has been locked in glaciers during ice ages and released when they melted. It has been underground for millennia and airborne for hours. The average water molecule spends about 9 days in the atmosphere before falling as precipitation. It spends roughly 2 weeks in a river, about 100 years in a lake, 3,000 years in the ocean. And if it is captured by a glacier or an ice sheet, it may be locked away for hundreds of thousands of years before being released. The water cycle operates across every timescale simultaneously, from the 9-day journey of a raindrop to the million-year imprisonment of an ice molecule deep in the Antarctic sheet. There is something calming about this, if you let it settle. The water that is in you right now, the water in your blood and your cells, and the tears you have cried and the breath you are slowly exhaling into the dark, is ancient. It has been part of this planet for longer than the continents have existed in their current arrangement. It was here before the first fish, before the first cell, before the first raindrop fell on the first ocean. It will be here when the last oceans evaporate, billions of years from now, when the sun expands and the Earth's story finally ends. You are borrowing it, briefly, and when you are done, it will continue without you, falling and rising and falling again, as it always has. The Amazon rainforest is not simply sitting in a wet climate, passively receiving the rain that falls on it. It is making the rain, actively, continuously, and on a scale that influences the weather of an entire continent. Every day, the trees of the Amazon release approximately 20 billion tons of water vapor into the atmosphere through a process called transpiration. Water is drawn up from the soil through the roots, carried through the trunk and branches, and released through tiny pores on the underside of the leaves called stomata. A single large tree can transpire over 1,000 liters of water per day. Multiply that by roughly 400 billion trees, which is the estimated population of the Amazon, and the result is a river of moisture flowing upward into the sky that is larger, in terms of volume, than the Amazon River itself flowing into the Atlantic. This moisture rises, cools, and condenses into clouds. The clouds produce rain. The rain falls on the forest. The forest transpires it back into the atmosphere. And the cycle repeats. The Amazon is a self-watering garden of continental proportions. A significant portion of the rain that falls on the western Amazon has already fallen and been recycled by the forest 2 or 3 times on its journey inland from the coast. But the system does not stay within the boundaries of the forest. The moisture travels. Atmospheric currents carry these so-called flying rivers southward and westward across South America, delivering rain to regions thousands of kilometers from the forest itself. The agricultural heartland of southern Brazil, which produces a significant share of the world's soybeans, coffee, and cattle, depends on moisture that originates in the Amazon. Bolivia, Paraguay, and northern Argentina receive rainfall that was generated by trees most of their inhabitants have never visited. This is why deforestation is not simply a local problem. When trees are removed, the transpiration stops. Less moisture enters the atmosphere. Less rain falls. The remaining forest receives less water, which stresses more trees, which reduces transpiration further. Scientists fear a tipping point, a threshold beyond which the forest can no longer generate enough rainfall to sustain itself. Beyond that point, the Amazon would not recover. It would transition, gradually but irreversibly, from rainforest to savanna. Current estimates suggest that approximately 17% of the Amazon has been deforested since the 1970s. Some researchers place the tipping point at 20 to 25%. The margin is not large, but the forest is still standing. The flying rivers are still flowing. Tonight, somewhere over the western Amazon, a cloud is forming from moisture that was pulled from the soil this morning by the roots of a tree that has been doing the same thing, quietly, every day for centuries. The rain will fall, the tree will drink. The cycle will continue as it has for millions of years, asking nothing from anyone except to be left alone. Pick up a handful of healthy soil. Hold it in your palm. It does not look like much. It is dark, crumbly, slightly damp, and it smells of earth in a way that is difficult to describe but immediately recognizable. It looks inert. It is not. That handful contains more living organisms than there are human beings on the planet. Bacteria in their billions. Fungi in networks so fine that a single gram of soil can contain kilometers of fungal threads. Nematodes, tiny transparent. Worms no thicker than a hair. Mites, springtails, and microscopic predators hunting their way through a landscape of mineral grains and organic matter that, at their scale, is as complex as any jungle. A single teaspoon of healthy soil can contain up to 1 billion bacteria, representing tens of thousands of distinct species. It is one of the most densely populated ecosystems on Earth, and it exists beneath your feet in a layer that is, in most places, less than 1 meter deep. Soil is not dirt. Dirt is what you sweep off the floor. Soil is a living system built over thousands of years through the interaction of rock, water, air, and biology. Rain and frost break rock into smaller and smaller fragments. Lichens colonize the surface, producing acids that dissolve the mineral structure. Over centuries, the fragments mix with decaying organic matter, forming a matrix that is part mineral, part organic, and entirely alive. A centimetre of topsoil can take between 200 and 1,000 years to form, depending on the climate and the parent rock. It is built with the same geological patience as a mountain, and it can be destroyed in a single season of careless farming. Beneath the surface, mycorrhizal fungi form partnerships with roughly 90% of all plant species. The fungi extend far beyond the reach of the roots, threading through the soil in every direction, accessing water and nutrients that the plant could not obtain alone. In return, the plant feeds the fungus with sugars produced by photosynthesis. It is a trade arrangement that has existed for at least 400 million years, since the earliest plants colonized the land. But the network does more than feed individual plants. It connects them. The fungal threads link root systems of different trees, sometimes different species, into a shared underground web through which nutrients and chemical signals can pass. A tree under attack by insects can send chemical warnings through the network, triggering defenses in neighboring trees before the insects arrive. Scientists in British Columbia discovered that the oldest trees, which they called mother trees, were connected to hundreds of others and appeared to direct resources toward their own offspring. The network has been called the Wood Wide Web, and beneath every forest floor it hums with a traffic of sugar and information that the trees above give no outward sign of producing. Charles Darwin, in his final book, published the year before his death, wrote about earthworms. He had spent decades studying them and concluded that few animals have played so important a part in the history of the world. Earthworms aerate the soil, drag organic matter deep underground, and pass earth through their bodies, enriching it with nutrients. He calculated that the earthworms of England moved tens of thousands of tons of soil per acre per century. It was an unfashionable subject for a man famous for finches and natural selection. But he was right. The thin layer of soil that covers the land surface of this planet is not a backdrop to life. It is the foundation. Remove it, and the forests collapse, the grasslands vanish, the crops fail. It took thousands of years to build. It is home to more biological diversity than any other environment on Earth. And it is contained in a layer thin enough to hold in your hands. The sky has no pigment. Nitrogen is colorless. Oxygen is colorless. There is nothing inherently blue about the gases that make up the atmosphere. And yet, you look up and you see blue, a soft, endless, convincing blue that has inspired poets and painters and children asking questions that most adults cannot properly answer. The answer is a phenomenon called Rayleigh scattering. Sunlight, which appears white, is actually a mixture of all visible wavelengths, from red at the long end of the spectrum to violet at the short end. When this light enters the atmosphere and collides with the molecules of nitrogen and oxygen, it is scattered in random directions. But the scattering is not equal. Shorter wavelengths are scattered much more efficiently than longer ones. Blue light is scattered roughly 10 times more than red. The result is blue light flung in every direction by every molecule it encounters, filling the sky from horizon to horizon. Violet light is actually scattered even more than blue, which raises the reasonable question of why the sky is not violet. Two reasons. The sun emits more blue light than violet, and your eyes are more sensitive to blue than to violet. The sky is, technically, full of scattered violet. You just cannot see most of it. At sunset, the light must travel through a much greater thickness of atmosphere to reach your eyes. The path is so long that nearly all the blue is scattered away before it arrives. What remains is the longer wavelengths, the reds and oranges and golds that pass through, relatively undisturbed. The sky near the horizon catches fire. It is the same light from the same sun, passing through the same air. The only thing that has changed is the distance, and the distance changes everything. On Mars, the sky is a dusty butterscotch pink during the day, because fine iron-rich dust scatters light differently. But at sunset on Mars, the sky near the sun turns blue. The dust particles are just the right size to scatter the longer wavelengths and let the shorter ones through, the exact opposite of what happens on Earth. A Martian sunset is a cold, pale blue disk sinking into a pink sky. It is beautiful in photographs and profoundly alien. The color of your sky is not a given. It is a consequence of the specific atmosphere surrounding the specific planet you happen to live on. Every world with an atmosphere has its own version of a sunset. None of them look like yours. The Earth is not silent. You cannot hear it, not with your ears, not without instruments, but the planet produces sound continuously. A low, deep, constant vibration that has been humming beneath the threshold of human perception for as long as the Earth has existed. Seismologists discovered it by accident. They were studying earthquake data, filtering out the sharp spikes of seismic events to isolate the background noise. And they found that even in the absence of any earthquake, the Earth vibrates constantly. A faint, persistent oscillation rippling through the crust at frequencies far below what any human ear could detect. The source is the ocean. Waves striking coastlines and interacting with the seafloor generate pressure pulses that travel through the solid Earth, setting the entire planet ringing like a bell, struck so softly that the sound never quite fades. Right now, beneath you, the ground is trembling at a frequency of roughly 10 to 30 seconds per cycle, driven by ocean waves breaking on shores you may never visit. In 1952, the German physicist Winfried Otto Schumann predicted that the space between the Earth's surface and the ionosphere should act as a resonant cavity, like the body of a guitar amplifying the vibration of its strings. He was right. Electromagnetic waves generated by lightning strikes bounce between the surface and the ionosphere, and certain frequencies resonate, amplifying and sustaining themselves in a continuous pulse. The fundamental frequency is 7.83 Hz, with harmonics at 14, 20, 26, and 33 Hz. These Schumann resonances are powered by the roughly 100 bolts of lightning that strike the Earth every second, each one injecting energy into the cavity, keeping the signal alive. An electromagnetic heartbeat sustained by 100 storms, raging simultaneously across the planet at every moment of every day. There are other sounds if you know how to listen. Singing sand dunes produce deep, audible tones when wind moves the grains across each other, a sustained hum that can carry for kilometers across the desert. The frequency depends on the size and shape of the grains. Dunes in the Sahara sing at different pitches than dunes in the Gobi, each one tuned by its own geology. And in the far north, the aurora makes sound. For centuries, indigenous peoples of Scandinavia and northern Canada reported hearing faint crackling and hissing during strong auroral displays. Scientists were skeptical for decades. Then, in 2012, researchers at Aalto University in Finland placed microphones at the correct altitude and confirmed it. The sounds are real, produced roughly 70 meters above the ground by electrical discharge associated with the aurora's interaction with the lower atmosphere. The northern lights are not only visible. In the quietest conditions, they are audible. You are lying on an instrument, a vast, complex, continuously vibrating instrument that produces frequencies in rock and air and electromagnetic fields, powered by oceans and lightning and wind and the charged particles streaming from the sun. None of it is meant for you. None of it was designed to be heard, but it is playing, as it always has, beneath the silence of your room, beneath the sound of your own breathing, beneath everything. The earth hums. It has never stopped. The Mariana Trench sits in the western Pacific Ocean, a crescent-shaped scar in the Earth's crust, where the Pacific Plate is being forced beneath the Mariana Plate. At its deepest point, a narrow slot called the Challenger Deep, the ocean floor is 10,935 meters below the surface, nearly 11 kilometers. If you placed Mount Everest at the bottom, its summit would still be submerged by more than a kilometer of water. The pressure at the bottom is 1,086 bars. That is roughly the equivalent of having 50 jumbo jets stacked on top of you. The temperature hovers just above freezing. There is no light. There has never been light. The sun's reach into the ocean gives out entirely by about 1,000 meters. Everything below that depth exists in a permanent, absolute darkness that has persisted since the ocean formed. And yet, life is there. Snailfish, translucent and ghost-like, swim through water that would crush a submarine. Amphipods, small crustacean scavengers, thrive in enormous numbers, feeding on the organic matter that drifts down from the sunlit world above. A slow rain of dead plankton and fish remains that marine scientists have given the surprisingly poetic name of marine snow. Xenophyophores, giant single-celled organisms the size of your fist, sit on the sediment in clusters, their existence a quiet challenge to the assumption that single-celled means small. Bacterial mats fed by chemical seeps carpet the floor in places where hydrogen sulfide and methane bubble up through the crust. Only 3 crewed missions have ever reached the Challenger Deep. The first, in 1960, carried Jacques Piccard and Don Walsh in the bathyscaphe Trieste. They descended for nearly 5 hours, spent 20 minutes on the bottom, and saw, to their astonishment, a flatfish swimming past the window. Life at a depth the scientific consensus had considered uninhabitable. In 2012, the filmmaker James Cameron made the descent alone, spending 3 hours on the bottom. The third mission came in 2019. On the floor of the Challenger Deep, deeper than Everest is tall, in the most remote point on the planet's surface, a plastic bag was found. It had drifted down from the surface, carried by currents, settling through 11 kilometers of water. It is a small detail, but it is a difficult one to forget. We have been to the moon. We have sent probes to the outer planets. The deepest hole ever drilled, the Kola Superdeep borehole, reached 12.2 kilometers into the crust before the heat defeated it. We have barely scratched the surface of our own world. The deepest ocean and the deepest rock remain, for all practical purposes, beyond our reach. 2 forces have shaped the surface of the Earth more dramatically than any other. One builds, one destroys, and sometimes they trade roles. Volcanoes are the Earth's pressure valves, the points where the heat and energy of the interior find their way to the surface. Most of them sit along plate boundaries where subduction and collision generate the conditions for magma to rise. But some sit in the middle of plates entirely, fed by plumes of hot rock that rise from deep in the mantle like slow-motion blowtorches, burning through the crust above. Hawaii was built this way, island by island, as the Pacific Plate drifted over a stationary hotspot. The Big Island is the newest. The chain of older islands stretching to the northwest traces the path the plate has taken over millions of years, each island a timestamp in basalt. Yellowstone sits atop another such hotspot, and beneath it lies a supervolcano that has erupted 3 times in the last 2.1 million years. Each eruption covered much of North America in ash. The most recent, 640,000 years ago, ejected roughly 1,000 cubic kilometers of material into the atmosphere. For reference, the eruption of Mount St. Helens in 1980 produced about 1 cubic kilometer. A Yellowstone eruption on the same scale today would bury several states in ash, collapse agriculture across the continent, and lower global temperatures for years. 74,000 years ago, the eruption of Toba in Sumatra may have been even larger. Some geneticists believe it triggered a volcanic winter that reduced the human population to fewer than 10,000 individuals, a bottleneck so severe that the genetic evidence is still written in our DNA. Every human alive today may be descended from the survivors of a single volcanic catastrophe. We nearly did not make it, and the evidence of how close we came is carried in the cells of every person you have ever met. And then there is ice. The Earth's climate oscillates between warm periods and glacial periods, driven by small variations in its orbit called Milankovitch cycles. The shape of the orbit stretches and contracts. The tilt of the axis shifts slightly. The timing of the closest approach to the Sun drifts. These variations are tiny, but over tens of thousands of years, they are enough to tip the balance, thickening the winter snow until it survives the summer, compressing into ice, reflecting more sunlight, cooling the planet further in a feedback loop that builds ice sheets kilometers thick. The last ice age ended only 12,000 years ago. Ice sheets 3 kilometers thick covered Canada, Scandinavia, and Northern Europe. Sea levels were 120 meters lower than today. You could walk from England to France. The English Channel, the North Sea, and the Persian Gulf were all dry land. Woolly mammoths grazed on grasslands that are now beneath the waves. The world your ancestors knew looked nothing like the one you inhabit. 12,000 years is nothing in geological terms. The ice will almost certainly return. The Milankovitch cycles have not stopped. The question is not whether, but when, and whether anything we have done in the meantime will alter the timing. Deep beneath the surface, in places where water and rock and time have conspired without any human involvement, the Earth has built some of its most extraordinary structures. The Naka mine in Chihuahua, Mexico, sits 300 meters below the desert. In the year 2000, miners drilling a new tunnel broke through into a chamber that no one knew existed. Inside, they found crystals of selenite, a form of gypsum, growing from the floor and walls and ceiling in beams up to 12 meters long and weighing as much as 50 tons. They are the largest natural crystals ever discovered. They grew over roughly 500,000 years, nourished by mineral-rich water heated by the magma chamber below, in conditions so stable and so perfectly balanced that the crystals had time to reach sizes that seem physically impossible. The temperature inside the cave is 58 degrees Celsius with 99% humidity. Without protective cooling suits, a human would lose consciousness within minutes. The crystals exist in a place that does not want visitors. In Vietnam, Hang Son Doong is the largest cave passage ever measured. Its main chamber is over 5 kilometers long, 200 meters high, and wide enough to contain entire city blocks. It has its own weather system. Clouds form inside the cave, gathering near the ceiling where the moist air rises and cools. In places where the roof has collapsed, shafts of sunlight reach the floor, and jungle has taken root hundreds of meters underground, complete with trees and birds and insects. A self-contained ecosystem growing inside a hole in the earth. In Romania, Movile Cave was sealed from the outside atmosphere for approximately 5.5 million years before it was accidentally discovered by workers in 1986. The air inside is low in oxygen and rich in hydrogen sulfide and carbon dioxide. There is no light. There has never been light, not for millions of years. And yet, the cave is full of life. 48 species have been identified inside, 33 of which are found nowhere else on Earth. They survive not on photosynthesis but on chemosynthesis, bacteria deriving energy from the chemical reactions between hydrogen sulfide and the minerals in the rock. An entire ecosystem, completely independent of the sun, evolving in total isolation for longer than humans, have existed as a species. These places are reminders that the surface of the Earth is the part we know, the part we have mapped and named. But beneath it, hidden in the dark, the planet has been building things that no one asked for and no one expected, with a patience and a creativity that we are only beginning to discover. On nights when the conditions are right, the sky near the poles catches fire, not with flame, but with light. Curtains of green and red and violet ripple across the darkness, shifting and folding like fabric in a slow wind, brightening and fading and brightening again in patterns that seem almost deliberate, but are not. This is the aurora. The process begins on the surface of the sun. The sun is not a calm object. It is a roiling sphere of plasma that continually ejects streams of charged particles into space, protons and electrons moving at up to 800 kilometers per second. This is the solar wind, and it blows constantly, filling the solar system with a thin, fast-moving gas of electrically charged material. When the solar wind reaches the Earth, it encounters the magnetosphere. Most of the particles are deflected, but some are captured by the magnetic field and funneled along the field lines toward the poles, where the lines converge and plunge into the atmosphere. As the particles descend, they collide with molecules of nitrogen and oxygen, transferring energy that the molecules release as light. Oxygen produces green at lower altitudes and red at higher ones. Nitrogen produces blue and violet. The specific colors depend on the altitude, the energy of the particles, and the type of molecule struck. The result is a light show that can stretch across the entire sky, visible from hundreds of kilometers away, lasting minutes or hours. From space, the aurora forms a glowing ring around each pole, a crown of light that shifts and brightens as the solar wind fluctuates. In 1859, a solar storm known as the Carrington event produced the most powerful geomagnetic disturbance in recorded history. Auroras were seen in the Caribbean, in Colombia, in Hawaii. Telegraph operators reported sparks leaping from their equipment. Some telegraph systems continued to send and receive messages even after being disconnected from their power supplies, running on nothing but the electrical currents induced in their wires by the storm. If a Carrington-scale event struck today, the damage to power grids, satellite systems, and communications networks would be measured in the trillions. The aurora is not merely beautiful. It is the visible evidence of the Earth's magnetic shield doing its job, intercepting charged particles that would otherwise strip the atmosphere and sterilize the surface. Every ripple of green light in the northern sky is a reminder that the liquid iron churning 6,000 kilometers beneath your feet is still doing what it has done for billions of years, protecting you, silently, invisibly, except on the nights when the sky turns green, and the shield, for a moment, becomes something you can see. There is a bacterium called Deinococcus radiodurans that can survive 5,000 times the radiation dose that would kill a human being. When its DNA is shattered by radiation into hundreds of fragments, it reassembles the pieces within hours, accurately, without error, and continues living as though nothing happened. Scientists have called it the world's toughest bacterium. It has earned the name. It is not alone. The Earth is home to organisms that thrive in conditions so extreme that, until they were discovered, those conditions were considered incompatible with life entirely. At hydrothermal vents in the deep ocean, where superheated water erupts from the sea floor at temperatures exceeding 300 degrees Celsius, bacteria metabolize hydrogen sulfide to generate energy, forming the base of ecosystems that exist without any input from the sun. Giant tube worms, blind shrimp, and pale crabs cluster around the vents in communities that were unknown to science until 1977. Before their discovery, it was assumed that all life on Earth ultimately depended on sunlight. The vent communities proved that assumption wrong. In the acidic hot springs of Yellowstone, where the pH drops to 0 and the water would dissolve metal, archaea flourish, their cellular chemistry adapted to conditions that would destroy virtually anything else on the planet. 3 kilometers below the Earth's surface, in rock that has not seen daylight for millions of years, microbial communities survive on the faint chemical energy produced by radioactive decay. Their metabolisms are so slow that their life cycles may be measured in centuries. They are alive in the broadest sense, but they exist on a timescale that makes even geological processes seem rushed. Tardigrades, the microscopic animals sometimes called water bears, have survived the vacuum of space, temperatures close to absolute zero. Temperatures above 150 degrees Celsius, pressures 6 times greater than the deepest ocean trench, and radiation doses hundreds of times the lethal limit for humans. They accomplish this by entering a state called cryptobiosis, shutting down all metabolic processes and waiting in suspended animation until conditions improve. They have been revived after 30 years in this state. In the Atacama Desert, the driest place on Earth outside the poles, organisms live inside rocks, surviving on the faint light that penetrates the translucent stone. In Antarctic ice, bacteria remain metabolically active at temperatures far below freezing, their cellular fluids laced with antifreeze proteins that prevent ice crystals from forming inside their cells. And the deep subsurface biosphere, the microbial world living within the Earth's crust and beneath the ocean floor, may contain more total biomass than all the oceans. An entire shadow biosphere, vast and ancient and almost entirely unexplored, existing beneath our feet. Every extremophile discovered on Earth expands the range of conditions we know life can tolerate, and in doing so, it expands the list of places in the universe where we might look for it. If life can thrive in boiling acid, survive the vacuum of space, metabolize rock in total darkness, and endure frozen inside Antarctic stone for millions of years, then the universe may be far more alive than it appears. The Earth is not merely a planet that supports life. It is a planet that has demonstrated over and over that life will find a way into any space that does not actively destroy it, and sometimes even into those that do. every atom in your body was made somewhere else. The hydrogen, the lightest and most abundant element, was made in the first few minutes after the Big Bang, 13.8 billion years ago, when the universe was a hot, dense soup of energy and particles cooling rapidly enough for protons and neutrons to combine for the first time. Hydrogen is the original element. It is the raw material from which everything else was built. And it is still the most common element in the universe by an enormous margin, making up roughly 75% of all ordinary matter. The hydrogen atoms in the water in your cells are 13.8 billion years old. They existed before there were stars. Everything heavier than hydrogen was forged in the furnaces of those stars. A star generates energy by fusing lighter elements into heavier ones. It begins with hydrogen, crushing atoms together under unimaginable pressure and temperature until they merge into helium, releasing energy in the process. When the hydrogen in the core runs out, the star contracts, heats up further, and begins fusing helium into carbon. Then carbon into oxygen, then oxygen into neon, neon into silicon, and silicon into iron. Each stage burns hotter and faster than the last. A star that spends millions of years burning hydrogen will burn through its silicon in a single day. And when it reaches iron, the process stops. Iron is the end of the line. Fusing iron does not release energy, it absorbs it. The core, suddenly unable to support itself, collapses in a fraction of a second. The outer layers, falling inward at a significant fraction of the speed of light, slam into the incompressible core and rebound outward in an explosion of almost incomprehensible violence. A supernova. For a few weeks, a single dying star outshines an entire galaxy. In that explosion, in the searing heat and pressure of the expanding shockwave, every element heavier than iron is forged. Gold, silver, platinum, uranium, iodine. The heaviest elements on the periodic table are made in seconds, in conditions so extreme that they exist nowhere else in the ordinary universe. They are scattered into space along with the lighter elements that the star produced during its lifetime, forming vast clouds of enriched gas and dust that drift through the galaxy for millions of years, slowly mixing, slowly cooling, slowly waiting for gravity to pull them together again. Some of those heaviest elements were forged in an even more extreme event. When two neutron stars collide, the densest objects in the universe, smashing together at a significant fraction of the speed of light, the explosion produces a flood of heavy elements in quantities that dwarf even a supernova. In 2017, astronomers detected gravitational waves from a neutron star merger for the first time and observed the electromagnetic afterglow. In that single event, an estimated 10 Earth masses of gold were produced and scattered into space. Much of the gold on Earth, the gold in jewelry, in electronics, in the fillings of teeth, may have come from a neutron star collision that occurred before our solar system existed. You are wearing the debris of a cosmic catastrophe. 4.5 billion years ago, one of those enriched clouds of gas and dust began to collapse under its own gravity. As it contracted, it spun faster, flattening into a disk. At the center, the density and temperature rose until hydrogen began to fuse and the sun ignited. In the disk around it, the remaining material clumped together into planets, moons, and asteroids. The Earth formed from this disk, assembled grain by grain from the debris of dead stars, a second-generation world built entirely from recycled material. The calcium in your bones was made in a star that exploded before the sun was born. The iron in your blood was made in a star. The phosphorus in your DNA, the sodium in your nerves, the carbon in every organic molecule in your body All of it was manufactured in the interior of a star that no longer exists. You are not on Earth looking up at the universe. You are the universe, arranged into a temporary shape that can look up at itself and wonder where it came from. Carl Sagan put it simply: we are a way for the cosmos to know itself. The most distant thing you can see with your naked eye on a clear, dark night is the Andromeda Galaxy, roughly 2.5 million light-years away. The photons hitting your retina left Andromeda before humans existed. You are seeing ancient light with eyes made of ancient stars, standing on a planet built from the wreckage of ancient explosions, breathing air that was poisoned into existence by ancient bacteria, held in place by a magnetic field powered by ancient iron. Everything about you is old, everything about you is borrowed, and everything about you, every atom without exception, will be returned when you are done with it, recycled into the Earth, and eventually, billions of years from now, recycled into whatever the universe decides to build next. On the 14th of February, 1990, the Voyager 1 spacecraft, having completed its tour of the outer planets and heading toward the edge of the solar system, turned its camera around and took one last photograph of home. From a distance of roughly 6 billion kilometers, the Earth appeared as a tiny speck of light, less than a single pixel wide, suspended in a scattered beam of sunlight. It is one of the most famous photographs ever taken, and one of the most humbling. From that distance, everything you have ever known is contained within that single, almost invisible point of light. Every mountain, every ocean, every forest, every city, every person who has ever lived or died or loved or suffered or wondered about the stars. All of it on a mote of dust suspended in a sunbeam. The Earth is rare. We do not yet know how rare because we have not found another planet quite like it, but the list of things that had to go right is long enough to give anyone pause. It sits in the habitable zone of a stable, middle-aged star, close enough for liquid water, far enough to avoid being scorched. It has a magnetic field generated by a liquid iron core that has been running without interruption for billions of years, shielding the atmosphere from the relentless bombardment of the solar wind. It has plate tectonics, the only rocky planet known to have them, recycling its surface, regulating its carbon cycle, building the mountains and ocean basins that shape the climate. It has a large moon born from violence that stabilizes its axial tilt and drives the tides that may have been essential to the origin of life. It orbits in a solar system that includes Jupiter, a gas giant so massive that it acts as a gravitational shield, sweeping up or deflecting many of the asteroids and comets that might otherwise strike the inner planets. Its atmosphere is the right thickness, the right composition, the right temperature. Its oceans are the right depth, the right chemistry, the right salinity. Change any one of these factors significantly, and the result is a different planet. A planet without a magnetic field loses its atmosphere the way Mars did. A planet without plate tectonics cannot regulate its temperature over geological time. A planet without a large moon may have a chaotic axial tilt that makes stable seasons impossible. A planet without Jupiter may be bombarded so frequently that complex life never has time to establish itself. The Earth is not inevitable. It is not guaranteed. It is the product of 4.5 billion years of fortunate accidents, each one building on the last, each one necessary for the next, producing a world so precisely suited to life that it is easy to forget how improbable the whole arrangement is. The Fermi paradox asks a question that has no comfortable answer. If the conditions for life are at all common in the universe, and the universe is very old and very large, then where is everyone? We have listened for signals, We have searched for signs. We have pointed our telescopes at thousands of stars and examined the light passing through the atmospheres of their planets, looking for the chemical signatures of life. We have found nothing. The silence may mean that life is rarer than we hope. It may mean that intelligent life is rarer still. It may mean that civilizations tend not to survive long enough to make themselves known across the distances involved. We do not know. The question remains open, and the silence, for now, continues. What we do know is that this pale blue dot, this tiny speck of light in an ordinary corner of an ordinary galaxy, is the only place in the universe where we have confirmed that anyone is home. It may not be the only such place. The universe is vast beyond comprehension, and the odds that we are truly alone seem vanishingly small. But until we find evidence to the contrary, this is it. This is the one we know about. And everything that has ever mattered to anyone has happened here. The Earth is 4.54 billion years old. It has been struck by an object the size of Mars. It has frozen solid from pole to pole. It has been poisoned by its own atmosphere. It has been split apart and reassembled by tectonic forces. It has been scorched by volcanic fire on a scale that nearly extinguished the human species. It has been struck by an asteroid that erased 75% of all living things. It has lost species by the billions, and it has grown them back. Its surface has been rearranged beyond recognition at least 5 times. Its climate has swung from hothouse to ice age and back again more times than anyone has been able to count. And through all of it, through every catastrophe and every recovery, and every long, quiet stretch of geological patience in between, life has persisted. Not the same life, not unchanged, but life in some form, without interruption, for at least 3.8 billion years. The thread has never broken. You are part of that thread. The atoms in your body were forged in stars that died before the sun was born. The water in your cells has been cycling through this planet since before the first continents formed. The oxygen in your lungs was produced by organisms that lived and died billions of years before anything with eyes existed to see the sky they were creating. You are not separate from the Earth. You are not a visitor. You are the Earth, briefly arranged into a shape that can lie here in the dark and think about what it means to be alive on a planet this old and this unlikely. The planet does not need you to understand it. It was here long before you arrived, and it will be here long after you are gone. The mantle will keep churning. The plates will keep drifting. The oceans will keep circulating their ancient water through the same slow loops they have been tracing for millions of years. New mountains will rise and old ones will erode to sand. The magnetic field will keep running, powered by the same liquid iron dynamo that has been spinning in the dark since before life began. The water cycle will keep turning, the same molecules falling and rising and falling again, passing through clouds and rivers and oceans and glaciers, and the cells of living things that have not yet evolved. The Earth is not fragile, though the conditions that allow us to live on it are. The planet has survived things that would end any civilization 1,000 times over. It will survive whatever comes next. The question is not whether the Earth endures. It always has. The question is what kind of Earth we leave behind, and whether the thread of life that has been running unbroken for nearly 4 billion years continues to include creatures that can look up at the night sky and feel wonder. But that is a question for the morning. Tonight, you are here, on this planet, in this quiet. Right now, as you lie here, the Earth is turning beneath you at 1,670 kilometers per hour. You feel nothing. It is orbiting the sun. At 107,000 kilometers per hour, you feel nothing. The entire solar system is moving through the galaxy at 828,000 kilometers per hour, carried along by the rotation of the Milky Way on a journey that takes 225 million years to complete a single orbit. You feel nothing. You are held in place by gravity, wrapped in a thin shell of breathable air, warmed by a star 150 million kilometers away, protected by a magnetic field generated by a churning ocean of liquid iron 6,000 kilometers beneath your pillow. Everything is moving, everything is in balance, and you are here, on the oldest, strangest, most beautiful rock in the known universe, breathing gently, listening to the story of the world that made you. Sleep well. Good night.